And next, we have Zhuolin Yang, a research scientist from Nvidia, to share with us about their reasoning models. Welcome, Zhuolin.
Thanks for the introduction, and actually, thanks, Zuri, for good introduction to the competitive programming. I'm Zhuolin Yang. I'm currently a NVIDIA research scientist, and I'm also an ex-competitive programmer. So here I plan to introduce our recently proposed model, the AceReason-Nemotron. This model is to try to show there's ability to build a strong IL model on top of the distilled model, and we can achieve the best state-of-the-art results on math and code reasoning benchmarks. So as an overview, here we have the best-in-class 14B reasoning model based on Q1 2.5, and we start from the initial SFT model, the DeepSeek R1 distilled model. And as we can just see from this figure, with just pure IL-driven methodology, the model's reasoning ability can have a large jump on both math and reasoning task and code reasoning task. The AMI and the LiveCodeBench score improved a lot. And the motivation of this work, one of the motivation of this work is that, so usually in the current reasoning agent field, we always do RL on some large-scale model. For example, we have DeepSeek R1, the Llama-Nemotron, and the Q13. However, for the small-scale model, especially under the 14B or 7B level, usually the RL models cannot have competitive strengths to the best SFT model. We're just curious to see that if we just use RL, if we can outperform the current best-in-class SFT model. And in this work, we demonstrate that, yes, we can do that with proper RL training recipe and carefully created RL data. So our training algorithms still lies in the standard GRP algorithms with some tricks from the double paper. We adopt the on-policy parameter update and remove the KL divergence term and the entropy loss term to stabilize the RL training process. And regarding for the data creation, we use the data from the modern competitive programming platform, including the LeetCode, and ASU. Beyond that, we set a very strict data filtering rules. First, we need to make sure that there's no data contamination and duplication across the data sources we use. So here is very important because in the current open source data set, there are a lot of overlaps. For example, there are a lot of overlaps between the tackle and the apps. Also, for the deep code data set, there contains a lot of overlaps, duplications in that. And we need to be careful about the data contamination and the possible data leakage. Also, we tried to make sure our test cases to each coding instance is strong and correct. This is verified by our golden solutions. Also, because if we need to do the code IL, we need to make sure that our reward, the verifiable reward, is robust and accurate. So we develop our own code verification tools beyond the LiveCodeBench default ones to make sure that the evaluation results is accurate. And we also exclude some code instances with multiple answer or interactive that is hard to verify the correctness. And we assign the difficulty to our RL training instances from 0 to 8 from a frontier large-scale large language model. In our training, we set the hyperparameters with appropriate learning rate, and also we do the curriculum training from the small maximum sequence to the large maximum sequence with different difficulty level. And we just adopted the binary reward and just a binary reward so the generated code will receive the positive reward if and only if it can pass all the test cases. So to help with the community, we also open sourced our training data and the evaluation toolkit in our Hugging Face repo. So I plan to share some insights in AceReason-Nemotron about how we managed to do this code IL improvements. So first insights we have is we find that the mass IL benefits the code IL. So specifically, we find that instead of start from the original distilled model, if we use mass IL as a warm-up, the model will be more stabilized in our training. So if we look at this curve, here the green curve refers to start with the DeepSeek R1's distilled model. And the purple curve refers to start with the mass IL warm-up model. So if we look at the green curve, the model is very sensitive to the hyperparameters and training noises. And at the end, it will just collapse. And also, we find that if we start from the distilled model, it will lack of some basic math knowledges, which are important to solving some hard competitive programming problems. If we check the red figure, here the red curve means we start from the DeepSeek R1's distilled model, and the green curve refers to start from the mass IL warm-up. So the red curve, the best score achieved by the red curve is obviously worse than the green curve. And to further dig into this, we checked how the mass IL actually improve the whole RL model training. So we find that doing the mass IL, actually it can enhance some math-related topics. So if we look at the upper figure, here the green bars refers to the model's improvements after the mass IL, and the blue bars refers to the improvements introduced from the code IL. So all the math-related topics like the number theory, the counting, and combinatorics are largely improved after mass IL. And the code IL will help more on some computer science, the implementation, the data structure related concepts, the topic problems. And I also checked some instances from the LiveCodeBench testing set. We found that there are some hard problems on AdCoder platforms actually requires heavy math-related knowledge. Without this knowledge, without the math IL, actually the model cannot solve this. And another interesting thing is that we find that the false positive and negative rewards really hurt IL. So here, the false negative rewards refers that the reward verification will judge the correct generation as incorrect. And there could be a lot of reason of having these false negatives. So first, if your verification tools is bug content, then you may have these false negatives. Also, it's possible that if your coding instances has some incorrect test cases, or you do not exclude some multi-solution coding problems. Here I will show some specific examples. So first example is the well-known the lead code problems, the two sum. So it's like you are given an array, and you need to find two elements of this array that they add them up to be the target number. So if so for some open source data sets, for example, the code R1's RL training set, there are some test cases they are generated through the LLM. Actually, it's invalid. That means there's no two elements in this array. The sum can be this target number. But this test cases is still added in their training data set if we do not do any verification and filtering. Also, if we check the Open R1's code forces RL training set, there is a problem that it's basically you need to construct a solution. And if there are multiple solutions, you can print any of them. But if we add this into our training set without the spatial judges, this will introduce some false negatives. That means in your local judge, given a correct solution, your generated code solution will be judged as incorrect. But actually, if we submit this into the official Codeforces platform, actually it's correct. And for the false positive reward, it's just to the opposite, that if your verification tool is bug contained, or your code instances with weak test cases, it will introduce the false positives. Here I will do another specific example in the TACO verified dataset. So in this problem, in this coding problems in this TACO verified dataset, the input limitation, the input is string of digit. And the length of the string should be at most 1e to 10 to the 5. But actually, all their test cases contains this input string. The length is within 20 or 40. So that means it will let some brute force solutions to pass or some incorrect solution to pass, which is not what we want. We did some interesting results on identifying how the false positive and negative rewards would hurt IL. As we can see in this curve, this green curve refers to our training set without any false positive and negatives. And this red one is with false positive, and this blue one is with the false negative. We find that if we train with the false negative rewards, the model will discard some correct reasoning traces during the training. And once on the testing set, if they encounter some testing problems that share the similar reasoning trace could help it to solve the problems, they will just discard it and cannot identify the correct solution. So the upper bound of our code IL score will be decreased. Also, similarly, if we train with these false positive rewards, the model will just take the shortcut. Model in training will think that, okay, I can pass this with a brute force solution or with some incorrect solution. And finally, they will get punished during the test set when the testing set has some strong test cases. So here's the main question: how to mitigate such false negative and such false positive reward? So first of all, definitely we need the bug-free reward verification tools as we just released. Also, we need to do the careful checking and aggressive filtering. We need to know what's the quality of our training instance and what's the verification results. Is the verification results matches the correctness of our generated code? Yeah, we need to put many efforts on that. And also, we heavily relied on the high quality data with the high quality test cases. So currently, the open source datasets suffers from such false positive and false negative rewards. So we may need some community efforts to create a good environment on continuously providing this high quality code IL training instances. Also, we found that the code IL can improve the pass at k over the SFT model. So we can see that if we check the bottom right figure, we evaluate the model performance from pass at 1 to pass at 1,000. That's a really large number. We can see there is a consistent gap between the RL model and the base distilled model with a consistent 10% drop gap. So this means that the RL not only enhances models' reasoning capabilities, but it can also push the limits of the model's reasoning abilities. Also, if we can see the instances that can be solved using RL compared to the base model, this green bars all shows the accuracy improvements of the RL model against the base model. So we can see that the RL actually unlocks a long tail of hard coding problems that the base distill model fails to solve within 64 attempts. And after applying this aggressive filtering and a good RL training recipe, we can see we achieve the best results compared to all open source code IO models. And here are some interesting future directions. The first is the high quality open source data for the code IO. So as I mentioned before, the current open source data suffers from the large overlap, the duplication between the open source data sets. Also, in these open sourced code IO data sets, this suffers from the low quality test cases. And this will result in the high false negative and false positive rewards. Some possible future directions are, so first is can we use the large language model to generate some high quality test cases or generate some high quality test case generator? I think there are some following up works are already doing that, and their generated test cases are proved to be strong. Also, is it possible to have some community-based data collection with humans feedback? Also, another thing is that we may want to have some deeper analysis on this transferable reasoning ability. So in our paper, we already show there is some transferable reasoning ability between the math and the code. And there are some other works showing this general reasoning abilities also can apply to the puzzle solving. The question is, do we have more? And how do these affect each other? And finally, we also want to have some real-world code agent beyond the competitive programming. Yeah, I think that's it.
Hey. So you mentioned in curating this high-quality data set, filtering based on overlaps and filtering low-quality cases. Have you all developed any ways of measuring the quality of a data set other than just running the RL training and seeing how it goes?
Yes, thanks for your question. So basically, these are all quite engineer work, right? And there's no automatic tools to measure the quality. I would just say if we have a golden solution, I mean the official solution, it can help a lot. Like if you have 10 correct official solution and 10 incorrect solution, you can identify the test case. Like if the set of test cases can fail all incorrect solution, then it must be it must be in good quality, right? And if there are some test cases that can fail even the official golden solution, then there must be some false negatives. That's what we're currently doing. But yeah, I think if there's some automatic way to evaluate the quality of the test case or evaluate the quality of the coding instances, it will be really great. Maybe some strong reward model maybe can do that, but I'm not sure. Yeah.
Cool, thank you.
Very interesting. Very curious at one thing. You mentioned how the first doing RL training on math helped you to initialize to do RL training on code.
Yeah.
Have you tried doing co-training on code and math together throughout instead of doing one and then the other?
Thanks for your question. In our work, we haven't tried that, but there are some prior work already shown that if we mix the code and math RL training, so there are several shortages on doing this. So first, the verification time of code RL is much longer than verification time of the math RL. So if we mix them together as a mini batch, that means the math RL instances always need to wait for the code RL instance verification. So this will slow down the whole RL training, right? Another thing is that in some prior works, they mentioned that response length of the math RL and the code RL is different. So if we mix them together, it will confuse the model. It will make the model to be confusing and actually result in some bad results. Yeah. And actually beyond that, I think maybe it's not bad to mix some math RL training instances with other general reasoning instances. I think this is meaningful. But yeah, but the current result shows that it's not that good to just mix the math and the code.
It seems to me that you were showing us a ground truth signal about whether there's bad data in the data set by the curves. So why can't you just use that to automatically figure out which ones are the bad data?
Yeah, thank you for your question. So we didn't release automatic tools to identify if this data is good or not. Instead, we open sourced verification tools to test if this generated code can pass all the tests or not. I think with these tools, you can build your own automatic tools on that.
I think we maybe have time for one more.
This is fantastic. Can this be reproduced with the existing Nemo skills kit?
I think we have the plan to do this, but since they are not fully settled down. Yeah.
I'm just curious if you've come up with any best practices for mitigating this problem with open source training data. Is there any quick and dirty solution to improve the outcome?
You mean improve the current open source training data?
Well, without fixing the data, if you've got, maybe a given quality data, is there a way to get better outcomes in your training? Like peer training or see high quality data first and then the open source data? Is there like a strategy?
I think we haven't done. I mean, we haven't done this strategy yet. Actually, current open source data set. I mean, to clean this or to blend this into it, it's a pain. It's a pain. Sometimes you need to do this deduplication or do this data cleaning. It's mainly based on your background knowledge or things, because which where this problem originated from, or how the strength of the test case. Then you can have an intuition on this data quality is good or not, and if we need to do some additional efforts. I feel like there's no automatic way to solve this. There's no good way to address these issues and solve it. Yeah, I would be really glad to see if later there are some researchers work on solving that. Yeah.
Thanks, Zhuolin, for sharing those insights.